thank you. It's really a pleasure and an honor to be here today. I teach in the University of Roma Tre in Italy. And before starting my speech, just a few words in German. Nur ein paar Worte auf Deutsch, auch Goethe-Institut zu danken. Ich habe Deutsch in Goethe-Institut Boppard gelernt. Es war 1986, so vor 40 Jahren. Aber die Zeit in Boppard war wirklich wichtig für mich. So, danke, vielen Dank. And now to my presentation, which will be, of course, in English. I'm used to speak English in conferences around the world, but I must say this time I am a little bit terrified because I think it's the first time that I have an audience which specialized precisely in assessing how awful my English is. But, okay, I will try to avoid thinking about that. My presentation will be split in two sections. The first one is an introductory one about some basic concept in artificial intelligence, neural networks, Gen AI, which is generative artificial intelligence. And the second one is on some problems connected with, in a way, philosophy of language, the problems of meaning in large language models. You may think that the second part is more relevant for you, but I always insist, I did also with Nick here, to have an introduction with basic concepts, because yes, everybody's talking about large language models those days, but quite often the discussions, you can see that there are basic concepts missing. So it's very important to have the basic. Maybe many of the things I will say are already familiar to you, but if they are not, take this as a test. This means that that it is also important for you to study a little bit how those systems works and not just how to use them. So I will start from the very beginning. It was working perfectly just a couple of minutes ago. Yes, it's the green one. I have tried. Okay. This is Alan Turing. And this is the very famous paper by Alan Turing on computing machinery and intelligence, 1950. This paper is still highly relevant because one of the points that are discussed in the 1950 paper by Turing is still highly relevant. The very beginning of the paper, Turing says, okay, I want to discuss the problem, can machine think? Is it possible to have intelligent machines? But first of all, we should discuss what thinking is, what intelligence is. And this is not an easy question. And Turing makes a philosophical move, which is a very sound one. Instead of trying to discuss from a theoretical point of view what is intelligence, let us try to give an operational definition of intelligence, in which situations we attribute intelligence. This is something which is still very relevant. Do we need a theoretical definition of intelligence, or do we need an operational one? From the point of view of Turing, the operational definition was the most sound way to discuss the problem of machine intelligence. And there is the famous Turing test, which basically is a test for the attribution of intelligence. The idea is, if I discuss with another person, to attribute intelligence, I don't need to check whether the brain is exactly like mine. I check the behavior, mainly the linguistic behavior, and this is the criterion to attribute intelligence. Another very important foundational moment is 1956. Turing, as you probably know, died in 1954, committing suicide. But in 1956, the people who had started working on artificial intelligence met in Dartmouth in the USA. And you can see a sort of original bias of artificial intelligence, which is quite clear. They are all white, males, professors or researchers in the United States. I think this is also relevant because their conception of intelligence was a very normative and a very logical, maybe too logical one. Now we say that that period is the period of classical artificial intelligence, logic, symbolic artificial intelligence, GOF AI, good old-fashioned artificial intelligence. And the basic assumption, there are basically two relevant assumptions here. The first one, intelligence is based on language and on reasoning. So it's because we use the language and because we use logic, reasoning, that we are intelligent. This is not so obvious today. Probably it wasn't so obvious even then. But this is one of the basic assumptions of classic AI. And the second assumption is language and reasoning are rule-based. There are rules for language, there are rules for logic, and if we can find the rules, we can feed them to a computer, and we will have a computer, a machine, which can use logic and language as we do. And since the criteria is the criteria of using logic and reasoning, logic and language, if we can feed those rules to a machine, we will have a machine which is intelligent from the point of view of Turing. Unfortunately, this didn't work. Barwin Minsky, who was one of the participants in the 1956 Dartmouth meeting, in 1973 wrote quite clearly, okay, it's almost 20 years that I'm working on artificial intelligence. In those 20 years, the only intelligent thing I was able to produce was my song, while machines, the computers I'm using, are as dumb as they were 20 years ago. There is a sort of failure of this logical, linguistic idea of artificial intelligence, and the first AI winter, the first period in which, at the beginning, they had great hopes. Herbert Simon, another of the Nobel Prize, another of the participants in the Dartmouth conference, in 1956, thought that intelligent machines were just 20 years in the future. They were not. From this failure, there was a number of different paths, different theoretical paths which were explored in the following years, and the most important one from our point of view today are neural networks. Just a couple of words about neural networks. This is how a neuron is made. We have about 86 billion neurons in our brain. And basically, a neuron has a lot of inputs from the dendrites. It works on the input in some way, and then there is one output through the axon, which is distributed to other neurons through synapses, neurons terminal. So, from a point of view, a neuron is something similar to a information processing unit working with many inputs and giving out one output. Even before the starting of the discussions on artificial intelligence, a scientist in specializing in neural sciences, Warren McCulloch, and the logician Walter Pitts, proposed the so-called MP model for the neuron. This is the MP neuron. It's just a theoretical model. Their aim was not to build intelligent machines, but just to understand how our brain works. And the idea is, okay, it is probably an oversimplification, but we can think of a neuron as having inputs, and to make things simple, let us assume that they are binary inputs, 1 or 0, signal or no signal, a rule, and then one output, which is also either 1 or 0. So, for instance, we can have AND neurons. They give 1 as output if and only if each of the input is 1, or neurons, they give 1 as output if and only if at least one of the inputs is 1. As you can understand, if our neurons work this way, well, it's easy to think that we can have intelligent machines because, after all, from this point of view, our brain is a computing machine. Our intelligence from this logicist point of view is the result of the working together of billions of small computing machines. Of course, they were aware that this was an oversimplification, but it says something about how neural networks started. From this simplified idea of a neuron, in the 50s, mainly due to the work of Frank Rosenblatt, a researcher in experimental psychology, we moved to the perceptron. Neural networks today, in a way, are made out of something quite similar to perceptrons. What are the differences with the basic idea of neuron, of MP neuron? Well, we dropped the idea that the values are just 0 or 1. They are numbers in the range between 0 and 1. And there is something more, the weights. The weights are a numerical measure of the relevance of a given input for that specific neuron. For instance, if we are crossing the street, visual inputs are very relevant for us. So we give a high weight to visual inputs. And birds chirping, they are not so relevant, and we don't give a high weight. But if we are listening to music, then even small audio inputs are very relevant for us. So the neurons which we use listening music, they give a lot of importance to something to which the neurons that we use when we cross the street don't give importance. So the weight, while the value comes from outside the neuron, the input, the weight comes from inside the neuron and is the relevance of that particular signal for that particular neuron. But at the beginning, this was still deterministic. There was a threshold, a fixed trigger value. For instance, if the weighted sum of input is less than 0.5, then the neuron does not activate. There is no signal. If it is more than 0.5, then the neuron will activate. At the beginning, it was still deterministic. As you can understand, if we have deterministic neurons, well, we can understand what's going on in a neural network, because we can know for sure whether, with a given range of values and with given weights, whether that neuron will activate or not. The main change of paradigm is in the 80s, when instead of a fixed threshold for the activation of a neuron, we got a probabilistic activation functions. Is it reasonable to think that, for instance, 0.49, no activation never, and 0.51 always activate? Isn't it more reasonable to think that the probability of activation of a neuron grows with the growth of the weighted sum of inputs? Moving from deterministic neurons to probabilistic ones changes everything, because even given a single neuron, we cannot predict for sure whether that neuron will activate or not. We can give probabilities, but we cannot predict for sure. This is why sometimes we say neural networks are black boxes. We have hundreds of millions of neurons, for each of which behaves in a probabilistic way. They are not really black boxes, because we know the values, we know the weights, we can choose the activation function. They are more like gray boxes. We know a lot, but not enough. Now, this is Hinton, one of the researchers which was behind. There was actually a double paradigm shift in the 80s. The first one is moving from deterministic to probabilistic neurons. The second shift is moving from single layer of neurons between the input and the output to deep neural networks, where we have many layers of neurons and signals, data can move forward and backward in the neural network. And this was done in the 80s. From the 80s onward, neural networks, mainly from the 90s, neural networks quite quickly became the main line of research in artificial intelligence. At the beginning, they were used mainly for discriminative tasks. For instance, we can train a network with a lot of images of cats and dogs. We can teach in this way the network to discriminate between cats and dogs. And when we give a new image without a label, the neural network can, if it has been trained on many images of cats and dogs, it can discriminate and tell us if the new image is that of a cat or of a dog. Those are discriminative neural networks. Even Rosenblatt at the beginning tried to work with a discriminative neural network. We will find on YouTube a wonderful black and white video from, I think, 1958, when Rosenblatt was trying to teach a neural network to discriminate between male pictures and female pictures. There was also a lot of bias in this and that idea, but it's quite funny because you can see that when you have very typical pictures, the networks can discriminate. And then when we have people with long hair or judges, they cannot discriminate because the hairs are apparently were very relevant in discriminating between those images. Anyhow, discriminative neural network, especially now that we have this kind of probabilistic and deep neural networks, work very, very well. And we get immediately a question which is quite natural. Since it is possible to teach to those networks to discriminate, is it also possible to teach to those networks to produce new images? Not to put a label on a given image, but to produce a new image of a cat or of a dog, different from the images on which the network has been trained? And the answer is yes. Those are generative neural networks. They don't put labels on content that we have produced, they produce new content. So the idea is that a discriminative neural network can label an image, while a generative neural network can produce an image. Now we will focus on large language models. Of course, as you know, we have systems which produce images, sounds, multimodal models which work with different kind of codes. But we will focus on large language model. And there are three concepts which are key to understanding how large language models work, which are training, tokenization, and embedding. Training, we use, you will know this, we use huge corpora of texts, huge textual corpora to train the network. Those texts, which may be documents, web page, websites, books, everything we can find with words, we give to the network. And the first thing which is done is tokenizing. What is a token? A token is a word or a meaningful part of a word, usually meaningful. We can also work with non-meaningful tokens, but usually it's a meaningful part of a word. For instance, dog is a token, cat is a token, today, somehow, 2 tokens. And then for each and every token, the system builds an embedding, a numerical representation of a token. To understand this idea of embedding, which is very important, we will use the example of the animal space. Here we have names of animals, basically. And we are confronting them on 2 dimensions, size and cuteness. So, for instance, mosquito is very small and it's not cute at all. There were medieval treatises on why did God create mosquitoes. So, mosquitoes, we don't like mosquitoes, we don't like tarantula. Crocodiles, they are bigger. They are slightly less awful than mosquitoes, but we are rather worried by crocodiles. So, elephant, the elephant is very big, but it's cute. We like elephants. So it's up there. And of course, we have puppies, kitten, which are the most cute of all. As you can understand, we can represent those 2 dimensions with numerical values. For instance, the value for cuteness for the elephant is somewhere probably around 68 or something like that. And the size value for elephant is up there, something like 92 or something like that. In large language models, those dimensions are always in the range between 0 and 1. And in large language models, we have 32 numbers after the dot. So high precision. And the system builds those numbers itself, by itself, in unsupervised training. What it does is to build up a number of dimensions. We have here only 2 dimensions, but in today's systems, we have thousands of different dimensions, for some of which we can roughly understand what they represent. Somewhere there is cuteness, somewhere there is size. There are also dimensions which the system builds, and we don't know exactly why, but it works. So each token, each word, is represented by thousands of numbers, each of which represent a different semantical or syntactical feature of that word. And the system builds those numbers by reading and rereading its training corpus and doing this kind of operations, next token prediction, or masked language modeling. In this way, it takes a sentence out of its corpus, masks a word, and tries to guess it. This morning, I have been Beaten by a terrible, is it possible to have been beaten by a terrible, for instance, book? No. The relationship between terrible bite and book is 0. But mosquito, bee, then we have probabilities. Everything is numbers inside, but numbers which represent semantical ways in which we use the words. At the beginning, this worked well enough in short texts. The systems were able to produce short, meaningful text, but when the text became longer, the system forgot the first part of the text. There was a problem of memory. In 2017, this paper by a number of Google researchers, Attention is All You Need, this paper, in a way, solved the memory problems. And the way in which this problem is solved is very expensive in computational terms. Every time a new token is produced, the system reconsiders all the context, all our prompt, all the context we have given to the system, reweights the probabilities in order to assess the probability of the next token. So basically, if we ask to a large language model, what can I do tonight? And the system tokenizes, what can I do tonight? And tries to produce one of the 3, 4, 5, depending on the temperature of the system, how creative we want the system to be, one of the most probable next token. So for instance, what can I do tonight? The token that is produced is 2. Then it puts 2 on the side of the prompt. What can I do tonight? Tonight you could go to the movie. They are next token predictors. The surprising fact is that with attention, if every time that a new token is predicted, the system reweights all the probabilities, this works surprisingly well. They are able to produce, as you know, because we all use this kind of large language models, they produce language in a perfect way. Now, there are many things that we should discuss, but there are 2 things which are quite important to consider: biases and hallucinations. They are 2 different concepts. Sometimes we tend to make a little bit of mixture of biases and hallucination, but they are 2 different concepts. Biases are present in the corpus that we use. There was a lot of study on the 2 tokens, king and queen. In a way, they are symmetrical. The king is the husband of the queen is the wife of the king. But all the little numbers representing power are higher in kings than in queen. Why? Because we live in a masculinist society, a patriarchal society in which men have been more powerful than women. And this reflects in our textual corpora. And so when the system produces the little number for the embedding of king and queen, those numbers reflect the fact that in our textual corpora, kings are more powerful than queens. This is a gender bias, and we can discuss about a huge number of different kinds of biases. Luckily enough, we have many women now working in artificial intelligence. We are quite good, still not good enough, but quite good in recognizing gender biases. There are also many other kinds of biases, for instance, age biases. If you ask a system to produce the image of 2 people in love, it will be always 2 people, very young people. They will never produce 2 people 80 years old in love. There is no reason why, but this is an age bias. And then hallucinations, as I said, they have a different root. the system works on probabilities. It doesn't look at the world. At least basic systems work this way. The so-called one-shot systems, the systems that just look at probabilities. They don't check to see whether those probabilities are actually real. I have a favorite example. Till a couple of years ago, if you asked ChatGPT whether there was electric light in Florence in Middle Age, it answered correctly, no, because in its correlations, electricity is not correlated to Middle Age. So the answer was correct. But if you tried to ask which were the political, economical, cultural consequences of the introduction of electric lights in Florence in 1343, for instance, then this is a tricky question. It's just like a boy at school, or if the teacher asked me this way, maybe there were electric lights in Florence. And ChatGPT a couple of years ago, now it doesn't make the same mistake, but a couple of years ago, produced a wonderful alternative description of a medieval Florence with electric lights. Because given the way in which the question was asked, it seemed plausible to produce tokens. There were important consequences. And once the system starts hallucinating, since the hallucination becomes part of its context, all the next tokens are predicted on the basis of, and so once it starts, there is no point in trying to convince a large language model that something is wrong, because it's part of the context which he uses to produce next tokens. So we have those problems, but hallucination today are not so important. It's a lot of people speak a lot about system hallucinating, but deep research systems today, systems which before answering check information on the web and reason, use time to elaborate the information they have found on the web, that kind of systems, hallucination there may still be hallucination in very specific situations, but they are not such a big problem as they were just a couple of years ago. Anyhow, and now to the second part of, quite quickly, what about using these kind of systems, for instance, in teaching? Well, the first thing which is relevant is AI literacy. I think that if something of what I've said in the first part of the speech was not familiar to you, this means that even for us, there is a lot of need for AI literacy. And in school, in the universities, the first need is to explain, to understand how those systems work. I work a lot with large language models, but I try to spend half of the time in studying them, not just using them. We should understand better how this kind of things works. This is also necessary if we want to fight against biases, if we want sound systems, if we want systems which have an ethical, a well-studied ethical background. We need a lot of study. And this is not something that is just for researchers. If we don't try to understand better how those systems work, we will have no hope to participate in a political way in the process of building and using large language models. So it is a political need, that of having a basic understanding of how those systems work. So AI literacy is very, very important. And then there is, of course, a number I will not discuss. Those are all examples of teaching activities that can be done with large language models. I very much agree with the title of that paper on New York Times, do not ban ChatGPT, teach with it. We need to, in order to understand how those systems work, we need to use them. It's like trying to ban from schools mobile phones. There is no point in banning them. We should teach how to use them. Otherwise, the student doesn't use the mobile phone in the classroom, but immediately after, he or she will use it without any understanding of how to use it. And there are a number of activities. The main point, we also have problems, of course, with the use of large language models in contexts such as tests, assessment. I will not speak specifically about this here because there are a lot of talks which will discuss or have discussed this topic during the conference. But of course, this is all relevant. We should, in a way, include the use of large language models in the process because there is no point in trying to keep them out of the process. And there are interesting things that can be done. This is just an example of, this is a notebook LM, is the system by Google, which is very useful in, especially designed for the use in schools. And this is a knowledge-based, based on works by Jane Austen. And it's quite interesting to see. It's one of the pre-programmed notebooks that you will find in Notebook LM, giving a look to the things that this system can do, can help in understanding how to use them, also in teaching. But the very last thing I want to discuss is the problem of language understanding. Just few words. I will not go, this is a sort of presentation nested inside the presentation. I will have no time to discuss everything here, but there are two things that I want to discuss with you. The first one, I will skip the introduction. The first one is this one. In 1921, a number of researchers in the field of generative AI and large language models was asked the question, do you think that large language models understand the language in a meaningful sense, in an interesting sense of understanding? And those were the answers. 480 among the most relevant researchers in the field, no consensus at all. The answers, there were four possibilities. Yes, they do understand the language. Maybe, maybe not, not for sure. Basically, the answers went 25, 25, 25. This was 5 years ago. I don't think that there is a lot. If we were to ask the same question today, I think we would get more or less the same kind of answers. Because the difference is not in the technical capabilities of the systems, but it's in the philosophy of language, especially philosophy of meaning that we have. There is a sort of paradox, or at least an interesting aspect of our discussion in theory of meaning. In a way, large language models are a strong, very strong argument for the theory of meaning as use. As you know, in philosophy of language, in philosophy of meaning, we have different theories of meaning, but one of the most relevant, from Wittgenstein onwards, is the idea that the meaning is given by the use of terms. And if, in a way, large language models are a strong argument, because from use, they learn to use the language. If we have Turing's idea that it is the way in which the system behaves, the capabilities of the systems which are relevant, of course, yes, they do understand the language. They can use the language very, very well. On the other side, if we accept this idea, if we are in these situations, it becomes very, very difficult to say that the system is so much different from us. Yes, of course, it is different from the point of view of how it works inside. It works with 0 and 1 and probably our brain works in different ways, but in a way, the behavior, the linguistic behavior is very similar to us. So if we adopt the idea of language as use, which seems to be strengthened by the capabilities of those systems, it seems also that we have to admit that those systems do understand the language. I will not pretend to give you an answer here. I will stop here. But it's just to give an idea of why the discussion on large language models is so relevant also in today's philosophy of language, in today's philosophy of mind. There are a number of very interesting problems which can be discussed in this connection. I will leave you the QR code of this presentation. I will not discuss, as I told you, everything, but I will leave you the QR code. I've left also this part of the presentation because if anybody is interested, it can give a look. And I would stop here, but if there is, I think maybe we have time for 1 or 2 questions. I don't know. I'll leave it to 3 minutes. So a couple of very quick questions for our Q&A.
I have a quick question. First of all, thank you for a very interesting presentation. So even today, it is not uncommon to have ChatGPT give you an answer. Thank you. You get an answer from ChatGPT, and then you say, no, it's not. And then it says, oh, I apologize for my error. And then it gives you the correct answer. Why do we need to tell it to give us the correct answer? Why doesn't it do so from the very beginning? And what happens under the hood when we say, no, it's not?
Okay, this is an interesting question. First of all, I should say that when we speak about artificial intelligence, there was a panel on frequently asked wrong questions on artificial intelligence at the very beginning, and I think this is very relevant because quite often we use artificial intelligence at singular, thinking as a sort of unique system, or we speak just about ChatGPT. We have a number of different systems, and much of the quality of the answers we get depends, of course, from our prompt, of course, from the context, but also from the system we are using. So, for instance, ChatGPT with deep research behaves in a very different way than ChatGPT without deep research. Now, to answer your question, what happens is this. If the system produces an hallucination, for instance, this is usually because we are using without deep research. If there is a wrong answer, when we give the system the right answer, sometimes, of course, our answers becomes part of the context. It will have a high relevance for the system because it comes from the user, and the system is used to give high relevance to the user's input. So the system will try to answer differently, incorporating our objections, so to speak. But sometimes this is enough to correct the mistake. Quite often it is not enough, because the mistake itself, the hallucination itself, has modified the weights of the system in a way in which the answers are no more always reasonable. So when we have a system that starts hallucinating, my advice is to close the window and start again. When we start having hallucinations, those hallucinations, even if we try to correct the system, and even if it seems to give us a correct answer, became part of the context, and it's often pointless to try to convince a system to give us the right answers. Usually when we get a wrong answer, it is an indication that we have used the wrong system. So if we get an answer which is not satisfactory, either the prompt is not satisfactory, or the kind of system we are using is not the right one to deal with that kind of prompt. So the advice is also to understand the differences between different kinds of systems. There is another question. I don't know whether we have time.
Sadly, no, but I think during the coffee break, maybe.
Yes, we can discuss anything about during the coffee break. So, thank you.